Okay, hello everyone and welcome. Today in this week in lab, we're going to be covering the aldol condensation. Okay, and the aldol condensation, like the Grignard, is a very good reaction for forming carbon-carbon bonds. So you may have seen the aldol in the lecture, but we're going to do a brief overview of what the aldol is. The aldol condensation is the reaction of two carbonyl compounds under acidic or basic conditions to form an alpha-beta unsaturated carbonyl compound. And this carbonyl could be a ketone or it could be an aldehyde. So that's why we just write carbonyl, depending on what R1 is, whether it's an H or a carbon fragment. So in the aldol condensation, the nucleophile and the electrophile are both carbonyl groups. So whereas in a Grignard reaction, the carbonyl compound was always the electrophile, in an aldol reaction, either one could be the nucleophile or the electrophile. And that's something we'll go into. So in this example, this structure in black is our nucleophile. And then this structure in red is our electrophile. So let's assume we perform this reaction under basic conditions, say sodium hydroxide. So the first step in the reaction is for hydroxide to deprotonate this alpha hydrogen. So this position, one away from the carbonyl, is called the alpha position. So these alpha protons are quite acidic. They have a pKa of around 19 compared to water, which is around 16. So not too far off. So this is just acidic enough for OH to deprotonate it. Okay, and this lone pair will go on to the alpha carbon. What structure does this generate? It generates a special structure here. So we have an anion, a carbanion, and this is referred to as an enolate. Okay, and for reasons you'll see, the reason it's called an enolate is because when you perform a resonance and you push these electrons up, you can generate something analogous to an enol. In fact, if you perform the reaction under basic conditions, it would be an enol. But here, it's going to have a negative charge, so it's called an enolate. Okay, oops. And this is the good nucleophile for our reaction. Okay, so let's redraw it here. So R1, I'm going to redraw it as the carbanion, and it really doesn't matter for the purpose of the mechanism which structure you draw. In fact, resonance structures is just a weighted average of these two, so they are identical in that regard. But I prefer to use the carbanion form, simpler to use here. So, and what it's going to do is it's going to attack the electrophile here. So I'll draw the electrophile, and it's going to attack the carbonyl carbon, just as in a Grignard reaction. Okay, in doing so, it's going to form this compound, which is special. So here we go. So this is now a alkoxide. Okay, but specifically, this is a beta hydroxy ketone, or aldehyde. In this example, it's a ketone. Beta hydroxy ketone. Where does that name come from? So if this is the alpha carbon, this is the beta carbon. And when this becomes protonated, so I'll just draw a brief protonation step. So imagine this is getting protonated. You can see that now there is a hydroxide group, a hydroxyl group on the beta carbon. So we call it a beta hydroxy ketone. Okay, that's the intermediate for this reaction. Okay, the final step of the reaction is an interesting step. So what's going to occur is this hydrogen is still acidic at this site. So what will occur is another equivalent of base is going to deprotonate it and form an enolate again. So we'll redraw it here, R1, sorry, this is R1. OH, R2, R3, and then here is our enolate here. And then the final step is for this enolate to form a pi bond between the alpha and beta carbons. And in doing so, it kicks off this OH group as a leaving group. Okay, and that will generate our alpha-beta unsaturated carbonyl compound. It's sort of difficult to conceive why hydroxide would act as a leaving group. After all, it's a strong base. So this mechanism is sometimes referred to as the E1CB, or E1 conjugate base mechanism. So it's sort of similar to an E2, but not exactly. It's not a concerted reaction, so OH will pick up H, form the carbanion, which will then eliminate and form a alkene here. But for our purposes, you can sort of think of it as an E2 reaction. But in reality, it's more akin to an E1CB going through a carbanion intermediate to form the compound. The term condensation may throw you off. The term condensation refers to the fact that water is generated as a product. So you can look here, this is the equivalent of water you generate. So H2O generated. And as you can see, water is in fact a byproduct. So OH will take this H, form H2O. Let's go over some mixed or crossed aldol reactions. So this is where we get into the delineation between ketones and aldehydes and how they interact in an aldol condensation. The problem being is that any compound with alpha hydrogen can act as the nucleophile in this reaction. So this could be the nucleophile or this could be the nucleophile, and vice versa. These could be the electrophile and this could be the electrophile. So let's consider all the different reactions that could occur in this hypothetical example, and we'll say it's a base catalyzed reaction. So on the left column, we have our nucleophiles. So we're going to say this is the nucleophile column. So hypothetically, these are the structures acting as nucleophiles, and these are the structures acting as electrophiles. So we'll draw them as the carbanions. So assume that there's a negative charge on each of these, and we'll go through each of these to see what products we generate. So in this first example, acetone is reacting with this aldehyde. It's called acetaldehyde. Okay, push electrons up. We're going to emit proton transfers to be brief. So in this example, we have this beta hydroxy ketone. And then after elimination, so this hydrogen will come off, form a pi bond here. We're going to get this structured. So keep that in mind, this alpha beta unsaturated compound. This is if our theoretical reaction occurs as we would expect. But if you mix these chemicals, you'll get this side reaction where acetaldehyde is now the nucleophile and acetone is the electrophile. So this will get kicked up, and it may seem that it's going to generate the same product, but it's actually not. So acetaldehyde is now attacking. Okay, now we have a tertiary beta hydroxy ketone. It's a bit different, and after elimination, we're going to form a tri-substituted alkene as our product. So H was taken away, double bond formed, and then now we have, you can see they're different compounds, methyl here, no methyl here. Now let's try this example. So these are examples of so-called crossed aldols or mixed aldols, where the nucleophile and electrophile are different species. But in some examples, you have the electrophile and nucleophile being equivalent structures. So acetaldehyde attacking itself and acetone attacking itself. And these are sometimes referred to as homoaldol products reacting with itself. So in this example, acetaldehyde attacks an acetaldehyde molecule, generating this structure. Okay, and then it's going to eliminate, okay, to form that structure. Now it looks very similar to this one, but it's not. So this one is an aldehyde, whereas this one's a ketone. So they're different. And then finally, if you have acetone that reacts with itself, so now it's going to attack there. Okay, and then it eliminates, and we generate this structure. And excuse me, I should have written an H here to keep it as an aldehyde. It's an aldehyde. And you can see these two are analogous, but they are in fact different. This is a ketone, whereas this is an aldehyde. So we have an issue here. We have one desired outcome, one desired product for our reaction, but here we're generating 4 different products. So selectivity in an aldol in this case is very low. So there's ways to get around this. There's ways to reduce the number of side products we have. And the solution to that is to use non-enolizable substrates. So remember, only an enolizable substrate can act as a nucleophile. So if we make our electrophile non-enolizable, in other words, it doesn't have alpha hydrogen, then we can have selectivity and reduce the number of side products. So here we have 3 examples of non-enolizable. So all 3 of these are non-enolizable, which means they have no alpha hydrogen. So there's no deprotonation possible on these substrates. So if you look at the alpha carbons of these substrates from left to right, this one doesn't have any alpha hydrogen here. It's a phenyl, and then here it's a terp-butyl group, so there's no hydrogen. Here, this is an aldehyde, so this H is not acidic. And here, this alpha carbon doesn't have any hydrogen. And in this example, so this is also there's no hydrogen here, no alpha hydrogen. Here there is in fact an alpha hydrogen, but it's not very acidic because it's an alpha beta unsaturated ketone. So these hydrogen have very low acidity compared to the saturated form if it was not a double bond. So, but if it is a double bond, it's not very acidic, so therefore it is non-enolizable. So here's two examples of non-enolizable reactions. Let's consider acetone reacting with tert-butyl acetaldehyde. So it's going to attack here. And as you can see, this can only act as the electrophile because there's no way there can be deprotonations on this substrate. So it only interacts as the electrophile. Okay. Oops, pen's running out here. So it's only going to act as the electrophile. Okay, so there's our beta hydroxy ketone. Perform an elimination step. Okay, and we generate this product. Now let's take another example. So here we have acetone, the same nucleophile. This is nucleophilic because it has alpha hydrogen. This right here, benzophenone, doesn't have any alpha hydrogen, so it can only interact as an electrophile. So here we go, it's going to attack. It's going to form the beta hydroxy ketone intermediate. Oh, here's our hydroxide, and then here's our two phenyl groups. Okay, and then after an elimination, we generate a single product. So you can see these are the only substrates you could have in this reaction. There could be theoretically a homoaldol with acetone, so acetone will react with itself, but that's typically negligible compared to the reactivity. These prefer to react with non-enolizable electrophiles. So that is our non-enolizable substrates. Okay, now we're going to cover some retrosynthesis problems of aldol products. So in your lecture course, you may encounter certain problems where you're presented with the product of an aldol, you're presented with an alpha beta unsaturated ketone or aldehyde, and you're asked to show the starting materials of what it came from. So the technique for these sorts of problems are to first identify the alpha and beta carbons. So in this example, here's the alpha carbon, one away from the carbonyl, here's the beta carbon. From here, we know that the intermediate is a beta hydroxy ketone. So we simply open the double bond going backwards. So retro means backwards. We're going backwards to the beta hydroxy ketone. So OH, and there we go. So we can still label our carbons to make sure we know what they start from. Okay, so here's our beta hydroxy ketone intermediate, and we know that the new carbon-carbon bond that is formed is between the alpha and beta carbons. That's the new bond that's being formed. So if we're going backwards, that's the bond that had to be formed, and if we're going backwards, that's the bond that was broken. So now we know that it came from these two substrates, acetone, and simply what you do is on the beta fragment, you simply turn the hydroxide group into a ketone or aldehyde. So just imagine the H popped off and now it's a pi bond. So in this example, we have that ketone as our electrophile. Okay, so for this example, we have a cyclic ring with a double bond, and normally this indicates that it was a intramolecular aldol reaction. So we can do as before, label the alpha and beta carbons and put an OH on the beta carbon. So this is going backwards. So now our OH is on the beta carbon. We'll keep them labeled alpha and beta. Now we draw a line between the alpha and beta carbons and turn the beta fragment into, in this case, an aldehyde. Okay, and that's what it came from. Make sure this H is not bonded to this carbon. This is a CH3 here. Okay, and as you can see, this is a tethered compound. So the reaction here was intramolecular. So this carbon attacked that one to form a six-membered ring. This example is similar. So here, alpha and beta. We're going to go backwards and put a hydroxide on the beta carbon. So this is the beta carbon. Here's the beta. And now we can draw a line between the alpha and beta carbons, disconnect them, and then put a ketone or aldehyde on the beta fragment. So it's going to look like this. There you go. And these sorts of intramolecular aldol reactions are characteristic of the Robinson annulation when you go over that in lecture. Okay, and then finally in this example, here's the alpha carbon, one away from the carbonyl. Here's the beta carbon. Okay, here's my OH on the beta carbon, alpha and beta, and now we're going to cleave the bond. Okay, and then turn the beta fragment into in this case, a ketone. And those are the two fragments it came from. This was actually a homoaldol between cyclopentanone and itself. So it was both the nucleophile and the electrophile. Let's go over now some of the more interesting aldol chemistry we find perhaps in daily life, depending on how frequently you cook. This compound here, gingerol, is found in, as the name implies, ginger, raw ginger. And this compound is a beta-hydroxyketone. See, beta-hydroxyketone. So it actually came from an aldol. And this structure is an analog to capsaicin. So capsaicin, the compound responsible for the spicy sensation we have when we eat foods with peppers in them or other spicy foods. So raw ginger, if you've ever bitten into raw ginger, it's fairly spicy. Not exactly the same as capsaicin, but it still has a similar sensation. Now, what's very interesting is when you manipulate raw ginger, depending on what you treat it with, it will become more or less spicy because of some aldol chemistry that occurs. So if you cook raw ginger, what occurs is a retroaldol reaction. Retroaldol. And I want to distinguish, this is not the same as our previous page. We're not going backwards and saying this was made from that. This is going forward in time. So when you cook it, this is what's occurring, a reverse aldol forward in time. So what occurs is this pi bond swings up, grabs the H from the hydroxyketone. These electrons come down to form the pi bond, and then this bond is returned to the alpha carbon. So that's the mechanism for a retroaldol. Okay, and then it just takes a while to redraw everything. So here's our carbanion portion, and then here's our side product. So this is hexanal, and hexanal actually has a fruity flavor, so also contributes to the flavor, but this is what we're interested in, our carbanion. And if you can envision, this carbanion is just going to grab an H and become protonated, so it basically gets rid of the charge. This new compound we generate is called zingerone, and zingerone is actually less spicy than capsaicin. The reason being is because structure influences function, and as you can see, zingerone is much less analogous to capsaicin. It no longer has this long, greasy tail, hydrophobic tail here. We've now cleaved it off. And because of that, it doesn't fit into the receptor as well. If you'll remember, the capsaicin fits into the TRPV1 receptor. We sort of mentioned that when we were discussing eugenol last semester. So zingerone is less spicy when you cook ginger, say in a stir fry or in a cooked dish. Another interesting thing occurs when you dehydrate ginger. So when ginger manufacturers make dehydrated ginger or powdered ginger that you might buy in the spice aisle at the supermarket, what occurs is actually a dehydration. So this is actually like the second step in an aldol reaction where some sort of a base, perhaps it's water in this case, there might not be sodium hydroxide when they're making dehydrated ginger, but it's going to deprotonate this H and perform the E1CB, but I'll just draw it as a simple elimination, E2, to make it simple. Okay, and we generate this product here, an alpha-beta unsaturated ketone. This molecule is called shogaol. And this compound is actually more spicy than gingerol. And the reason being is by performing an elimination, we've made this structure more analogous. It's more similar to capsaicin. And that's because capsaicin lacks this OH group. So you can sort of envision that this is structurally similar to capsaicin versus the gingerol, and is actually more spicy. So if you make ginger snap cookies or something with baked ginger, it actually has some of that spicy quality to it that you don't get with cooked ginger. So some cool aldol chemistry is definitely relevant in our daily lives. Finally, we're going to discuss our experiment, which is fairly straightforward. In this experiment, we're taking acetone and p-anisaldehyde. You'll notice that this is non-enolizable to the benefit of our yield. And we're going to react it with sodium hydroxide, and we're going to generate dibenzyl acetone as the product, or something analogous to a dibenzyl acetone product. This structure motif, where you have this acetone in the middle and they have double bonds conjugated to rings, are similar to the compounds used in sunscreens because they absorb UV light very well. Light can interact with these conjugated pi systems very well. And in this reaction, if we go over the mechanism, we're doing it under basic conditions. So we're going to deprotonate. This is going to form our nucleophile, our enolate. This is going to attack the carbonyl of the p-anisaldehyde. Okay, here is the beta hydroxyketone you generate. Okay, and then finally you perform the elimination. So I'll just draw it as an E2, even though it's not an E2. Simple elimination. And now we generate the alpha-beta unsaturated ketone. Now you'll notice that this structure doesn't look exactly the same as this dibenzyl acetone, and that's because it has to go through one more round of this to get to the dibenzyl acetone. So it reacts on one side of the acetone using this alpha carbon, and then it will react a second time using this alpha carbon on the left side with another equivalent of p-anisaldehyde. So it basically reacts twice, and we form our product. And this product is yellow, okay, due to the conjugation in its pi system. Okay, so I hope you enjoyed that. We'll see you in the lab. Okay, so we're going to do our Aldol reaction. Our reaction vessel is a 125 milliliter Erlenmeyer flask. You'll notice the setup is much simpler compared to the Grineer last week, and the addition of the reagents is also much simpler. Our solvent is acetone, so we've got 30 mils here. So we'll place our acetone in the flask. So this is our reaction solvent. Okay, here is our p-anisaldehyde. You can see it's a light yellow, and we're going to be using about 4 grams. The exact amount will be given on canvas. And typically when you perform this in lab, you would use a smaller scale, but we're going to try doing a bit of a larger scale for the recrystallization. It might work better. So no fuss here. We're just going to add the p-anisaldehyde. Okay, so we'll give it a brief stir here. Make sure it's dissolved. And interestingly, as we know, acetone is both a solvent and a reactant in this reaction. So it's a solvolysis reaction. It will participate in this reaction. So to get the aldol to start between the acetone and the anisaldehyde, we're going to add our catalyst, which is sodium hydroxide. This is 1.8 grams dissolved in 3 mils of water. Okay, and that's it. So we're simply going to let this stir at room temperature for about an hour. And over the course of the reaction, the mixture should turn yellow as the formation of the product increases. Okay, it's been stirring for a little over an hour. You can see that it's nice and yellow, fairly dark. So we're going to stop the stirring. And to precipitate our product, remember our product is the dibenzyl acetone, we're going to pour this mixture into some cold water here. So you can see there's a little bit of residual ice. So as the acetone concentration goes down and it's mostly water, it should precipitate the dibenzyl acetone as the product. So we're just going to dump quickly into there. And then we'll use some water to rinse out the flask. Okay, there we go. I think we'll add a little more water too to make sure there's so little acetone that it precipitates from the solution. Okay, now we'll stir this. Okay, and we also want to make sure that any chunks are broken up, so take a stir bar and agitate it. And let's add a little water, see if anything precipitates. Okay, so I think we've got it all crashed out of solution. So we'll let it stir for a few minutes just to make sure it's broken up, and then we'll filter. Okay, so we've let it stir for a few minutes and most of it has precipitated. So now we're going to take this precipitate and we're going to filter it. So okay, so we've let it dry on the filter for a few minutes, and now we're going to scrape it into this beaker here. So before we isolate it, we're going to recrystallize this product to make sure it's pure. So we're going to scrape, scrape, scrape. You can see it looks like there's quite a bit, so hopefully that's good. We did scale up the reaction, so we're expecting a few grams is our product here. As you can see, it's still fairly damp. So we also would not want to use this as our final product due to how wet it is. So we're going to try to see if we can get it into this beaker. We'll take the stir bar out before we get the rest of it. So yeah, it's kind of pasty, so a lot of water. Okay, so there is our crude product. We'll take the stir bar out and then we're going to recrystallize it. Okay, so we have our crude product here. I've measured the mass on it, so we actually have a tiered beaker here. I figured out that we have around 7 grams of crude. The rule of thumb that the literature says is to crystallize it from about 4 mils of ethanol per gram. So we have around 7 grams, so this is about 28 mils of ethanol, 95% ethanol. So it's going in here. Okay, and the goal is we're going to heat it up until everything dissolves, and then we're going to cool it, or take it off the hot plate to let it cool and hopefully crystals form. In recent years, we've had trouble getting this crystallization to work for various reasons, so hopefully this works out. So we'll also try another technique. We'll seed it. We'll show you that is we'll seed it when we take it off the heat. So place it on there. We'll turn on the stirring, help it dissolve. So that dissolved quite easily. Looks like we're going to have to boil it to remove some of the ethanol to make sure we have a good yield. If you put too much recrystallization solvent, when it cools, too much of it will remain in solution and your yield will be low. So we'll boil off some of the ethanol here. All right, so we've boiled off some of the ethanol. I think we're about ready. So what we're going to do is we're going to take it off the heat. I'm going to remove the stir bar with a magnet, and then I'm going to add 1 boiling chip. So sometimes when things don't want to crystallize, you can add a boiling chip or any irregular piece of glassware, piece of broken glass, porcelain, and what it does is it gives the molecules something to cling on to. So maybe this will help get it to crystallize. Okay, so here we go. I'm going to remove it from the heat. I'm going to carefully remove the stir bar. Clean that after. And then here's our boiling chip. So it looks like our boiling chips didn't work as well. We're going to try to seed it with a little bit of residue here, so you can see there's some solid. This is not the pure solid. It's the impure solid just on the spatula. So ideally you'd want to use a pure sample of this and kind of put a small little piece of that solid, a piece of that crystal. But you can try to sort of dip temporarily just briefly dip this into the solution and it might cause it to crystallize. I think it's super saturated. See, it's something oiled out. That might be it, actually. The product might just melt. Yeah, but that's more akin to an oil. It's not really. I mean, you can kind of see when I tip it, and then you see the residue here is oily. I don't know if that's the anisaldehyde. Not really. See, look, it almost looks like it's biphasic here. It's more akin to removing the solvent at this point than actually recrystallizing. Yep, and there you go, solidified. All right, so our crystallization didn't work too well. So we had to basically remove most of the ethanol, and then we added some toluene, and toluene seems to have sort of worked. So we heated the toluene, let it cool, and we sort of got, well, we have a solid. I don't know if you would call them crystals, so this is not ideal. Ideally, the crystals are nice long spears or needles, but this is more of an amorphous solid, so the purity here is not going to be as good, but it looks better than with the ethanol. With the ethanol, the solid was much darker, so here it's a much lighter yellow, akin to what we would expect for the product. So we're going to filter it now, and we've got some cold ethanol to help us get through, to wash things through. Okay, and then there's the product. Those are the two boiling chips. We'll take those out. So, yeah, it looks like we might have lost quite a bit in the filtrate here. You can even see perhaps a layer where the ethanol is probably layering out, or a little bit of toluene is layering out at the top. So we'll see how low it is. Hopefully it's not too low. Take our spatula here. We wipe it on a paper towel, clean it a little bit. Okay, take out the boiling chips. All right, that looks like we're all going to get out. That's all we're going to get from the filter. So that's all. probably be a very low yield. That's it. So we'll place this in a desiccator for just a little bit. There's very little water probably in here, and then we'll get a yield. All right, so here's our product in here. The mass of it is about 100 milligrams, 0.1 grams, which is incredibly low given the scale we're working on. And to account for that, if you'll recall, we added a certain amount of ethanol based on our crude mass, so how much solid we collected immediately after the reaction, and we had about 7 grams. There's some water in there, but we're in the gram level, so there were substantial losses here. We've gone from perhaps 5 grams down to 0.1 grams, and that is most definitely accounted for the washing step. So when I washed it out to try to wash out the crystals with cold ethanol, the cold ethanol actually dissolved it quite a bit, and you can see the residue on here after the ethanol evaporates from the walls of the beaker and it leaves a residue. So there were substantial losses, even from using cold ethanol, which is supposed to be dissolve as little as possible. So we'll definitely need to revisit the crystallization step of this experiment sometime later. Anyway, you can use that value to calculate your yields, 0.1 grams. It'll be low, but you can do it nonetheless. All right, so we've got a mass spec of the product here. The mass spec shows two peaks, which we can identify. This one here at 177, and then this one here at 295. The product mass for the desired product, the dibenzyl acetone, is 294. So this 295 is M plus H, so it just gets protonated. That's what gives you the extra 1 AMU. That's what that is. This one at 176 we think corresponds to the monobenzyl product. So in other words, the acetone has reacted with one PNS aldehyde on one side of the acetone, but it has not yet reacted on the right side. In other words, the reaction didn't go to completion, and this may be it. Maybe we didn't let the reaction run long enough. So if you let it run longer, in theory, you generate more of the product, and perhaps the product is what's really insoluble. And if it's really insoluble, then that will lead to better recrystallization. Instead, what dissolves is actually this impurity, it could be. And we're not sure about this 375 peak or this 610 peak. Alrighty, but in other words, we did make some of the product at least, so that's good.